And this is the topic of my presentations today. How close are we to the reality? With showcase of two project applications. One is the modeling of the concrete infill steel pipe pile, and the other one is modeling of RC wall failure in soft clay. We are a consulting firm specialized in geotechnical engineering. Our office is based in Kuala Lumpur, Malaysia. We undertake all kinds of geotechnical design and analysis uh, in Malaysia and the nearby countries. If you want to know more about my company, you can visit our company website at www.totoassociates.com. This is the content of the talk today. Basically, I will share two project applications uh, using Midas GTS NX. The first project applications will be the numerical modeling of steel pipe pile with and without concrete infill. It is not the purpose of these presentations to show you the pile group analysis, but we take one step backwards to go into the fundamental of the problems to show you how to model the settlement behavior of a single pile in axisymmetry model and compare the result against the main test result. The second example will be a numerical simulation of a failure of RC wall in one forensic investigation. These two examples have one similarity. That is, the system has reached some form of failure or yielding. And these examples are good case histories to test the program in terms of the modeling of the stiffness and as well as the strength. And after that, I will draw conclusion. Now we go into the first part of the presentations, the numerical modeling of concrete infill steel pipe pile. This is the layout plan of the bridge that connecting one small island here to the mainland of Sarawak, our partnership entities in Malaysia. So what I'm going to show you today is a simulation of a maintenance test of a steel pipe pile carried out offshore. And this is the location of the test. This is the part of the long sections of the bridge. There's one pile group for every 200-meter distance across the river. And for each pile cap, there are 30 number of steel pipe piles. This is the SPTM plotted against the depth from the nearby boreholes. The soft clay on top is about 10 meter, and below the soft clay is load silt with increasing SPTN starting from about 6, increase slowly to SPTN more than 50 at about 70 meters. The steel pipe pile stop at the top of the hard layers, and the figure on the right illustrates the blow counts during the pile driving in orange color line. And you expect a sudden spike of blow counts here after halting the driving operations for say 1 day, but generally the blow counts is consistent with the SPTN value. This is a typical drawing showing the steel pipe pile and the um, infill concrete, and we expect some soil plugging near the pile toe. If you refer to ICP methods, the pile is 1.5 meter diameter, is big enough to have some soil plugging, and we concrete the steel pipe pile with grade 40 concrete above the soil plugging. And before we go into the numerical modeling, let's have a look at some of the photo taken at the site. These photos were taken during the installation of the steel pipe pile using 45-ton hammer installed from the barge. And this is a setting up of the counterload of the MLT test. And this is a close-up of the load cells for the testing. And now we go into the FE analysis. This is the mesh simulating maintain load test of steel pipe pile. Quadrilateral elements were used for this problem. The size of the the model is 30 meter in width and approximately 107 meter in depth. The concrete infill was modeled by changing the soil properties from the soil to the concrete, and the soil was modeled by using more Coulomb model, assuming friction angle of 29 degree, following the recommendation by ICP methods. And we model the increasing stiffness with depth of the subsoil by having a few layers of soil with different shear modulus that relate to the SPDN using these equations. These equations was developed from a 100 instrumented test pile. You can find the derivations from this paper. The mesh was densified along the pile and soil interface, where the gradient of the stress is intense, and the size of the mesh is gradually increased towards the right boundary. The diameter of the steel pipe pile is 1.5 meter diameter, and we only model half of the problems, 0.075 meters, and the thickness of the steel pipe pile is 19 mm. Now this is the gist of the simulations. We introduce interface element for the outer face of the steel pipe pile and inner face of the steel pipe pile. To simulate the soil give way on the pile surface when it is sheared. By introducing the interface element, we then can limit the developed shaft resistance, in which we can link the analysis to some codes that is specially developed for steel pipe pile, in which I will explain in the following slides. And I will show you what happens if we don't model the interface element when I show you the results of the analysis. There are few methods to estimate the shaft resistance of the steel pipe pile. For example, ICP method, UWA method, NGI method, Fugro method, Purdue CPT methods. In this analysis, we computed ultimate shaft resistance by referring to ICP method. The ultimate shaft resistance is shown in this figure, and the exact value is given in the table on the right. And you notice that the ultimate shaft resistance is not increasing linearly with depth, and it increases exponentially when it comes near to the toe. We assume that the ultimate shaft resistance at the inner face of the steel pipe pile is half of the ultimate shaft resistance at the outer face by referring to the Nordic codes and some measurement. Now we come to the construction stage. We use the fully coupled seepage stress analysis in this modeling. The construction stage is like this. Step 1, generate the ground stress. Step 2, install the steel pipe pile. And step 3, apply vertical load on the steel pipe pile in 200 steps in one day. And now we look at the results. This is a settlement contour of the model when the pile is loaded to twice of the working load. The pile settle 41 mm, and if you load a bit closer to the settlement of the pile near the pile soil interface, you will notice that the piles is actually settled much more than the soil, and it is actually sheared and give way, and the load is then transferred to the lower part of the soil. This is the load settlement curve of the pile. Surprisingly, the program was able to accommodate settlement up to 10 meters by using interface element. But what matters to us is the settlement within the allowable loads, as shown in the figure on the right. Plotted in the figures also the fractions of the load taken up by the pile tip. Now we compare the load settlement curve to the maintain load test. The blue color lines in figure 1 is the simulated load settlement curve as presented in the previous slide. The black color lines here is the load settlement curve obtained from the maintain load test, and they are perfectly matched. Now we look at the load settlement curve of the steel pipe pile without concrete infill in the figure number 2. Apparently, the load settlement curve is much softer for steel pipe pile without concrete infill compared to the concrete infill steel pipe pile. The yellow color line in figure number 2 here is the simulation using Midas GTS NX for the steel pipe pile without concrete infill, and the orange color line is the simulations using the ICP methods. And they compare well with the Mendel test results given in the green color lines. And now we look at what happens if we disregard the pulsar interface in the modeling. The load settlement curve for the analysis without using the interface element is represented by dotted line in red color for the red color, this line, for steel pipe pile with and without concrete infill in figure 3 and figure 4 respectively. It's very clear that the ultimate bearing capacity is over-predicted without considering the interface element. This is because the soil doesn't have the slip mechanism if the interface is not introduced. And now we look at the developed vertical stress at the pile tip here and below the concrete infill surface plotted against the applied load at the pile top. Figure 6 is just the blow up for figure 5 for lower range of the applied loads. The stress developed below the pile tip is about 2.6 times higher compared to the vertical stress developed below the concrete infill surface. The rate of load picked up by the concrete infill is slower than the pile tip, which come later stage in the loading. And the pile tip carries more load than the concrete infill surface due to the shading effect in the steel pipe pile. And this is the distribution of the vertical stress across the pile tip. You can see that the vertical stress developed within the soil plug over the applied vertical loads. And now we look at the vertical stress developed below and across the concrete infill surface here. Similar to a trend at the pile tip, the vertical stress developed below the concrete infill surface increase over the applying loads at the pile top. And now we look at the evolutions of the loads in concrete infill steel pipe pile plotted against the applied load at the pile top. And now we look at the figure 11. The applied load is initially taken up by the shaft, and it is gradually transferred to the base as the applied load increases. And in figure 12, roughly about 97% of the load shared by the external face of the steel pipe pile compared to only 3% taken up by the inner face of the steel pipe pile. And now we look at figure 13. Roughly about 52% of the base load taken up by the steel pipe pile compared to 48% taken up by the soil plug. And now we can draw the load transfer mechanism from the simulations of the finite element analysis. The bearing capacity of the pile is the summation of the load taken by the external and inner face of the steel pipe pile and the bearing load at the pile tip and below the concrete infill. So this concludes the first part of my presentations. Now we go to the second part of my presentations. That is the simulation of a failure involving pile-supported RC wall in soft clay. And this is the chronological event of the failure. A RC wall was constructed in 2005. After 5 years, some cracks were observed on the RC wall facade. And within the period of July to November in 2010, the owner constructed a swimming pool behind the RC wall. And at that time, some further cracks were reported. And the RC wall collapsed in December 2018. Some photograph of the failure. The RC wall was translated forward and rotated. And I'll show you the failure mechanism in a short while. The swimming pool is intact, and the surface around the swimming pool is tile, which tells that there's no rainfall infiltrations into the ground. And this is the front view of the failure. This is a survey plan, layout plan of the problems. Superimpose also the extent of the 3D model. And cross sections 2 is here. The failure happened here. This is a cross section 2 which cut through the collapsed RC wall. The boreholes and the Macintosh prop indicate the presence of the soft clay. And the trial pit results indicate that the failed material is soaked. The RC wall is supported by 2 rows of RC pile, 200 by 200 mm in size and 9 meter in length, spaced at 0.9 meter centers at the front row and spaced at 1.8 meter centers at the rear. And we also found that there were no drainage layer constructed at the back of the RC wall. Referring to Hong Kong Geo Guide 6, It is good practice to provide drainage layer behind the RC wall, which I will show you later how the water build up behind the RC wall and then cause the failure. And this is the soil water characteristic curve in our modeling. To model the unsaturated flow, you need this information. To model the flow of the uh, leakage from the swimming pool to the RC wall. The fill material is mainly sealed, which is represented by the blue color lines in this figure. This SWCC curve basically just tells you that how able is the soil to retain water in the soil. We also check the SWCC of our model to the result reported by some researchers from NTU, and the curves are comparable. And this is a deduced failure mechanism after gathering some information from the stakeholders. The mode of failure was initially translational, and followed by toppling after the stem of the RC wall broken. We have ruled out few possibility of the failure. We thought that it is not a global instability because the failure did not happen immediately after the completion of the RC wall. This is similar to the embankment filling when where the factor of safety is lowest at the end of the constructions of the embankment and increases with time as the soil consolidates. We also rule out that it is caused by the power installations during the constructions of the swimming pool behind the RC wall, a distance away, because the lateral displacement from the installations will continue to happen in months, not after 8 years. And the floor was tile, and therefore the rainfall infiltration is not possible. There's one very important information provided by the stakeholders that they measured the leakage at the water meter that connected to the swimming pool, and they found that there were leakage of 3 liters of water per hour into the swimming pool. And we think that possibly the failure could be caused by the leakage, as the moisture content of the fill after the failure was as high as 40%, while the surrounding fill, exposed fill, was actually dry. And we will verify our hypothesis by the numerical modeling. And now we come to the modeling part. This is the three-dimensional finite element model with indications of the subsoil layering. And we have to use fully coupled effective stress analysis because these simulations involve consolidation process in soft clay due to the filling, and also the unsaturated flows in the unsaturated fill. We model the soft clay using modified chemical clay model and sandy soils with hardening soil model. And it is very important to back calculate the industrial strength in your model by running a triaxial simulation in the software, so that the industrial strength that you simulated is somewhat similar to your field venture test. And now we come to the construction stage of the simulation. Step 1, we generate the ground stress. Step 2, backfill to create the working platform. Step 3, install RC pile and construct the RC wall. Step 4. Step 4 to step 9, gradually fill up the fill to platform at RL 11. And step number 10, construct the swimming pool and consolidate for 4 years. And step 11, we then can model the leakage by applying the nodal flux at the edge of the swimming pool. And also there is a report of leakage of the pipe behind the RC wall, and therefore we apply also a nodal flux behind the RC wall. And these are the results. This is the movement of the RC wall and the RC pile after constructing the swimming pool and before the leakage. And the following few slides will show you the movement of the RC structures after 1, 2, 3, and 4 years of leakage before the computation start to diverge. And now we look at the phreatic surface before and after the leakage. These slides show you the phreatic surface before the leakage. That is the initial water table. And this is the phreatic surface after 4 years of leakage. And you can see that the water table is rising behind the RC wall and impose the lateral pressure on the wall and push forward the RC wall, and followed by a failure. And now we compare the load in the pile and the wall to the allowable and ultimate envelope of the structure capacity. And indeed, the bending moment in the RC pile before the leakage is still within the allowable envelope, which ties up with the site observations. And the bending moment in the pile developed as the leakage prolonged, and finally reached the failure envelope and initiated the failure. However, in the bending moment in the RC wall, as shown in the figure 2, is still well below the failure envelope. And this figure shows the bending moment profile developed in the RC pile. And the maximum moment is actually happen at below the clay layer. And we also carry out some a few parametric studies to understand the effect of the positions of the leakage to the failure. And these are our observations. Number 1, if the leakage is further away from the heel of the RC wall, the heel of the RC wall is here, such as shown in the figure in the case 1, the phreatic line at the heel of the RC wall is low, and therefore you will not initiate a failure. Number 2, if the leakage is near the heel of the RC wall, the phreatic line at the heel of the RC wall is high, and therefore the water pressure will push forward the RC wall and initiate a failure in case 2. Right? And number 3, if the leakage is right behind the RC wall, the phreatic line is highest within the RC wall but remain low at the heel of the RC wall, and therefore it will not initiate a failure. The weight of the water will be carried by the pile as a axial load. And this is a plot of stresses in the field at the heel of the RC wall before the leakage in figure 3 and after the leakage in figure 4. The pore water pressure is represented by orange color line and is initially negative in the field and it turns to positive after the leakage. And now we look at the figure number 4. The black color dotted line is the total stress calculated by the effective stress soil mechanics uh, formula, assuming a Ka of 0.36 here. And if we integrate the pressure, and we get the total lateral force of 62.85 kN per meter. And if we integrate the effective lateral stress and the pore pressure from the Midas GTS NX here, this line and the water pressure, we get the total lateral force of 79.74 kN per meter. In other words, if the engineer did not provide the subsoil drainage behind the RC wall and designed the pile using the total stress following the um, effective stress soil mechanics uh, and assume there's no pore pressure, the pile may be under design. And now I would like to share with you one phenomenon in fully coupled stress analysis, that is the Mendel effect. The rise of the water table is not solely due to the influx itself, but partly due to the formulations of the fully coupled effective stress. Wong and colleagues have demonstrated the problem in one large triaxial, where the sample was saturated to half of the height of the sample and load the sample from the top under confining stress. The load is initially taken largely by the saturated soil in the form of excess pore pressure and then dissipate over time. During the process, the water in the saturated soils will flow upwards and form a new water table. And therefore, sometimes you will see the water table rises in fully coupled effective stress analysis, and the conditions become more severe when the soil become more sandy. So with that, I would like to draw the following conclusions. Number one, fully coupled seepage stress analysis, or normally we mention as a fully coupled effective stress analysis, was employed in 2 project applications. Number 2, it is vital to model the power soil interface for accurate load settlement predictions in terms of the settlement and also the bearing capacity. The performance of the Midas GTS in predicting a load settlement curve of the steel pipe pile with and without concrete infill is reliable. And number 3, it is demonstrated that Midas GTS NX is able to model the unsaturated flows and the consolidations process using full coupled effective stress analysis, and the results tie up with the observations, especially on the mode of failure, on how it's translated and rotated. And also the reasoning of the failure is also very uh, uh, ties up with the simulations and the observations.